Actually, yesterday I gave a wrong name. The क्या हुआ ये? क्या हुआ? क्या लाइट उड़ी गया क्या? ये तो आ ही नहीं रहा कुछ इसमें। नहीं आज लाइट आ रही है क्या? दिख तो रहा है कुछ नहीं रहा। लाइट तो अब आई कुछ फ्लैश। क्या हुआ? Well, okay, one thing I missed out actually. Yakut was a postdoc with Orzag. So the person whom we used to call God was Orzag, not Yakut. But Yakut, I think, came from Russia, and so a lot of work which was done on RNG was the Russian work. Orzag, of course, I don't know if some of you may, if you, there's a very nice textbook on mathematics, on asymptotic methods and other things, higher topics, Orzag and Bender. So Orzag is known. So it was Orzag we used to call God Orzag, not Yakut. Yeah. Yakut, I think. Orzag was the professor at Princeton. हाँ मतलब ये और याकूत आया था तो एंड आई थिंक वो रशिया से पूरा लेके आया था. हाँ मतलब तो याकूत डिड मोस्ट ऑफ द वर्क, दैट्स व्हाई. Orzag is probably not American, it's not American, but maybe is, I don't know, उसकी फैमिली में कब शिफ्ट हुए, whether he shifted or his parents shifted. Anyway, all Americans are probably from somewhere else, other than the real Americans who have been उनको कैद करके रिजर्वेशंस में रख दिया गया है. हैं? कौन? ट्रम्प. हाँ. ORSZAG. No, of course, as I've already said, while we are, it says lecture 36, I think in a lot of lectures we have gone over time. So overall we would have had, as far as time goes, we would not have had less than 42 lectures. If you count a 50-minute lecture, that you can check up by the video and adding up all the minutes if you want. So, okay. So we talked about the K-epsilon model in the last class. So today's class, I'll just sum up some of those things and let's see what to. So we have K epsilon is the simplest complete model of turbulence. So you have any problem, any new problem, anything you want to do flow simulation and you expect the flow to become turbulent, you can use K epsilon model. It will, some constants are there, but they have already been prefixed. So at least you will be able to get some sort of a flow simulation using K epsilon method. But then we do know there are some this thing that the standard K epsilon over predicts the rate of spreading of a round jet. If you look at a round jet, the rate of spreading is over predicted, and this can be remedied by adjusting the values of C epsilon 1 and C epsilon 2. So you can, for different type of flows, things don't match, you try playing with the constants and see if it works. Because see, eventually what will happen is, if you have to use it as a design problem, the design tool, then you may have to run many simulations. It's not just one. So for one, you set up to calibrate the constants and tweak them if they need be, and then use with those constants you run it for other cases. Of course, we are still not sure if the other cases do they further need tweaking, but then experimental data will not be available for all the cases because you are designing something. So then, if it works, it works. Now, certain modifications have also been proposed. For example, Pope in 1978 added an extra source term in the equation for dissipation, and this term was of the form mean of Sij, mean of omega jk, mean of omega ki times k square upon epsilon. So depending on, and maybe this probably followed for the particular flow which he was trying to do, he may have realized that you need the rate of rotation also as an input. So people keep on coming up with this. Now there are other two equation models also. That instead of epsilon, for example, solve an equation for omega k times L, omega square and tau. So you could solve, the second equation could be something else, and then the eddy viscosity will be formed from this second quantity. So if you are solving instead of epsilon, you are solving an equation for omega, or you are solving it for k times L. L is some length scale. So effectively you are solving it for a length scale. Or sometimes there's omega, then you have it for omega square, and tau. Tau is a time scale. And what are all these terms? In particular, a popular model is k omega model, where omega is defined as epsilon upon k. Omega is a 1 upon time. It's so if you define omega as epsilon upon k, then the equation for omega is partial omega by partial t Now, once again, you have to keep in mind that the dimensional similarity has to be there. So there's a transport term, a production term, and a dissipation term. So omega is 1 upon t. So dissipation term would have been minus c omega 2 times omega, and 1 upon t will make it omega square. And similarly, the production term, it is this term times production, and then we match the dimension, so it becomes omega by k. Okay. Or what was the production term? It was in the Q. So it's another way of deriving these equations is if we look at the standard K epsilon equation. Then based on those two equations also, starting from K and epsilon equation, we can get, if we define omega is equal to, as we have defined here, epsilon times K to the power of minus 1. So then what I can do is, so I can, omega is equal to epsilon K to the power of minus 1. So d omega by dt partial will be equal to partial epsilon by partial t into 1 over k minus 1 over k square epsilon times dk by dt. So now I can substitute for d epsilon by dt and dk by dt from the k epsilon equations. And then I can get to this form of the equation. dk by dt, we have the equation for k and there's an equation for epsilon. So what I'm saying is, you have omega is equal to, what have we written here? Epsilon times k to the power of minus 1. So d omega or partial omega by partial t will be partial epsilon by partial t into k to the power of minus 1 plus or epsilon times minus 1. So this becomes minus times k to the power of minus 2 partial k by partial t. Okay, yeah. No, because I just want to write this omega term. What is, ये partial है ना? This left hand side is also partial. So I take the partial derivative of dt with of each of these terms. पार्शियल के वो मैंने शायद गलत लिखा था, नीचे वाला पार्शियल है ना. क्या हुआ, कहाँ गलती है भाई? ये वाला अरे वो तो ठीक तो किया था. पहले मैं डी लिख रहा था, देन आई रियलाइज्ड. Okay, so then from here you can work out, put partial epsilon by partial t from the epsilon equation. So here the what I'm saying is, any new quantity you want to derive, you can also go to the original k epsilon equation, and from there you can get these terms. Basically you have to now get rid of all epsilons. So wherever epsilon comes, you put it in terms of omega and k. तो क्या चीज? हाँ, so what not interchangeable. What I'm saying is, this is how you can also get another way to get the equation for omega. Okay, so that can be done, and you get this equation. हाँ, so you will put it by omega. Yeah, in fact, now when you are solving k omega equation, the epsilon there has to be replaced by omega. See, k normally we have to solve two equations. K will be always there in everything. The other equation could be for omega, could be for k times L, could be for omega square. So the different people have come up with these different things.
ये वाली इक्वेशन ड्राइव करने के लिए हमें एप्सिलॉन बाय k स्क्वायर डेल k बाय डेल t ये तो लिखने की जरूरत नहीं.
नहीं, तो अब तुम्हें डी के पार्शियल के बाय पार्शियल टी के इक्वेशन से जाएगी यहाँ पे.
तो वो सब्स्टिट्यूट करके,
हाँ, वो सब्स्टिट्यूट करके फाइनल इक्वेशन आएगा ना.
देखने से लग रहा है कि इसकी जरूरत नहीं पड़ेगी, बस डेल एप्सिलॉन में डेल t बाय k वही सब्स्टिट्यूट करने से शायद एप्सिलॉन वाली इक्वेशन में आ जाए.
नहीं, पर फिर ये तो अब नहीं पड़ेगी, देख लेना, एक आध टर्म एक्स्ट्रा आ सकती है. सी, I think the way we have derived this omega equation is exactly the way we derived the k equation. The epsilon equation. हाँ, but इस तरह से करोगे तो भी ये फॉर्म आ जाएगा. Maybe one extra term will come. So this is just to, maybe this is how people worked out when they first did this. So therefore, in fact, मैं बताता हूँ इसमें क्या आता है. If we follow this, एक मिनट, let me complete this then. And if we assume that sigma k is equal to sigma epsilon is equal to sigma omega, then the equation we get, or luckily Pope had done this for me, what you are asking. ये कांस्टेंट्स चेंज हो जाएंगे, बट देयर you also get an extra term. This is what I was saying, plus nu t over sigma omega k. If you follow the k epsilon equation route, then these three terms were what you had, but ये एक extra term आ जाएगी, वो probably second वाली.
ऊपर वाली इक्वेशन सिर्फ एप्सिलॉन वाली इक्वेशन.
ऊपर वाली तो जस्ट, हाँ, मतलब आपने जैसे एप्सिलॉन जैसे बनाई थी वैसे बना लो. नहीं तो ठीक है, यू यूज ईदर ऑफ देम. मतलब कौन सी करेक्ट का तो इन टर्बुलेंस मॉडलिंग एक्चुअली, एंड पॉसिबली दिस कुड आल्सो सो हैपन दैट in the limit of high Reynolds number this term may be negligible. You may also find that. But so equation, हाँ आप पूछो, somebody was saying ऊपर करो. Capital L is some length scale. So you are writing the second equation is being written not just for k times a length scale L.
But this is not necessarily any length scale that we have covered earlier.
No, so you're writing an equation for that. Nah? You're writing an equation for k times L. The second equation. Tau will be something like k upon epsilon. Tau is probably omega inverse. A turbulent time scale. So turbulent time scale will be k upon epsilon.
Like the same as
No, omega now is epsilon upon k. It's basically inverse time scale.
so it's only representative of the frequency.
Of a frequency.
And omega square is not strong.
No, omega square. This is just k upon. No. हाँ. ये मुझे नहीं, मैंने केवल किताब से उतारा है, करके देख लिया. एग्जाम में पूछूंगा, एग्जाम में डिराइव कर देना इसको. तो एग्जाम थोड़ा करना, एग्जाम में यही करना पड़ेगा. एग्जाम में यही डिराइव करना है. Okay. Now what one finds, but see what happens was, what I'm trying to say is when you do start from k epsilon model, so then you will get this c epsilon 1, c epsilon 2 which came there. And in the omega equation we just wrote them as c omega 1, c omega 2. तो इस तरह से होगा मतलब, तो but they are all constant. So in fact writing it this way can also tell you then how, what value to choose for c omega 1 and c omega 2. Often you may not know, but if you derive it from this, then you can say, okay, c omega 1 will be c epsilon 1 minus 1 and c omega 2 will be c epsilon 2 minus 1. So that way you can probably get some hint to start with. Okay, now k omega is the second most popular model in two equation models. This was Wilcox in 1993 gave this, and here nu t and k equation is the same, and we saw, except of course that instead of epsilon we'll put in the omega term, and are essentially the same. I'll use the word essentially to same, and we solve equation for omega instead of epsilon. And this model does well in near wall region and in flows with streamwise pressure gradient. If there is a streamwise pressure gradient, then this work out well. But here the boundary conditions on omega could be a bit challenging, because for epsilon the boundary conditions were 0 on the wall, omega will not be 0 on the wall. So then you will have to probably look into and how to tweak this. हाँ, इनफ्लोज में मतलब इसके रिजल्ट अच्छे आते हैं जहाँ पे स्ट्रीम वाइज प्रेशर ग्रेडियंट है, तो देयर you find k omega does a better job. In fact, there are more models. There's another model called the k epsilon v square, where v means तो v prime मैं कह रहा हूँ क्योंकि we have used turbulent. So for the what this is used for near wall flows, it works very well. Where in the wall region you also solve an equation for the vertical fluctuations v prime square. So basically it will be we write it as v square. In fact, it's called k epsilon v square, but it's a mean of v square. So different models, but then this becomes sort of a 3-equation model. But as we said, there was this another model which came, Spellart-Elmerath model, in 1994. And here we solve a model equation for nu t. So this is a one equation model because you are solving only one extra equation, and that equation is for nu t. So here we still have the eddy viscosity, but we solve an equation. So we remove the incompleteness of K model, and this model is computationally simpler than the 2-equation models. And here if you look at it, the model can be written as partial nu t by partial t plus mean of uj all the production and dissipation terms for nu t are clubbed together in the form S of nu. So basically here you are solving an equation for nu t only, and S this depends on nu t mean rate of rotation capital omega gradient of nu t, that is partial nu t by partial xj, and distance from the wall. So anyway, this is just the Spellart-Elmhorst model. It was developed. Spellart actually was probably still is work for Boeing. So he developed that model for flow past aircraft wings, and it performed well in external flows. But then we used this model. In fact, I also did. A couple of students worked on that. We showed that it also worked very well for internal flows. So in some sense, because basically what you are doing is you are trying to conserve quantities, writing conservation equations and forcing some sort of smoothness on the solutions through equations like this. And eventually what is right or what is wrong gets to be checked only by verification of the data. So this was another model. डायरेक्ट ये डिराइव नहीं है, इसका बेसिकली वही है जैसे एप्सिलॉन का इक्वेशन है वैसा ही न्यूटी का इक्वेशन है, बस उसमें प्रोडक्शन एस न्यू में सब कुछ मान लिया, सब कुछ आ जाएगा, प्रोडक्शन भी डिसिपेशन भी सब आ जाएगा. तो मे बी एस न्यू में नॉट बी अ सिंगल टर्म, इट मे हैव 2 or 3 टर्म्स.
उसमें एप्सिलॉन को कुछ न्यूटी की टर्म्स में सब्स्टिट्यूट करें तो इक्वेशन आ सकती है,
ऐसा कुछ तो नहीं, प्रॉब्लम आई डोंट नो. मतलब वैसे तो न्यूटी इज इक्वल टू के स्क्वायर अपॉन एप्सिलॉन है, नहीं न्यूटी, हाँ न्यूटी के टू द पावर ऑफ 3/2 बाय एप्सिलॉन, नहीं कैसे था, के स्क्वायर बाय एप्सिलॉन, तो के स्क्वायर बाय एप्सिलॉन हो गया न्यूटी. तो अगर हम के स्क्वायर बाय एप्सिलॉन का इक्वेशन लिखेंगे तो ऐसा आ जाएगा, तो न्यूटी का बन गया. मे बी दैट कुड अच्छा, मे बी आई विल ट्राई टू थिंक अबाउट इट. Look at k square times epsilon to the, in fact Pope's book gives a general this thing where you have different powers के लिए you can derive the equation of k and epsilon. So if you have a quantity z is equal to k to the power of a epsilon to the power b, so then you can derive the equation for z using k epsilon. So from starting from k epsilon, so then that way probably also Newton equation will come if you take it as k square upon epsilon. So yeah, this is basically production of Newton and dissipation of Newton. It's, yeah, it is not. So so it is like, yeah, so then it's like saying that if a quantity like Newton exists, which is basically, you think of it as a ratio of the Reynolds stress to the mean velocity. So then how will that evolve in the flow? So it is, no. नहीं, it's नहीं, Newton तो एडी विस्कोसिटी है ही. No, but coefficient of viscosity or no. There are a lot of differences because firstly, nu normally is a constant, but Newton is property of the flow, not of the fluid. So Newton is something which you have just created so that you can create, that is how Newton started with, so that you could tackle the same equations as you are doing it for laminar flow. Near the wall it will be 0 if the Reynolds stresses are 0, so then it will become 0. No, beginning I don't know. Well, it evolved. I think my understanding was that Newton always was considered as a constant across a layer in shear flows. It was not, it could vary with X, what we call as uniform. The first assumption we did here was uniform turbulent viscosity. So it is constant with Y but changes with X. So it is in some sense Newton is also a self-similar variable which we had talked about. Newton also could think of it. In general it's a function of X and Y, but in self-similar flows it will be a function of zeta, which is Y upon N. Okay. Okay. Now this was one stage. Now what I'm going to do in the is just as not even a flavor, but what are the higher levels of K epsilon, and all these are eddy viscosity models where you're solving for the mean velocity. Now on the other end of the spectrum, we have what we call DNS. Direct numerical simulations. This is the most advanced way of solving turbulence, and here what you are doing is just solving the Navier-Stokes. So here we solve the Navier-Stokes equations, which are resolved up to length scale of eta. At least you have to go up to Kolmogorov length scale. Then only you will have DNS. Now, one way of doing the DNS, or the obvious way which comes to mind, at least those who are familiar with CFD, what we do is we solve either using finite volume or finite difference the Navier-Stokes equations. Okay, so that means we approximate the derivatives in a particular way, that is finite difference. Finite volume, we integrate the equations over small volumes and get the derivative. But most of the DNS in turbulence is not done using that way. Now, at least in my group, at least the people with whom I collaborate and my ex-students and current collaborators from AMU, we are following, when we do DNS, we are just using the old tools. That means finite difference and finite volume. And we make the grid smaller and smaller, and that's why we are not able to go to very high Reynolds number. Because if we have to go to very high Reynolds number, then the grid has to be finer and we don't have those resources. But one way, and that's just as I said, I'll only give you a flavor. What you do is, most of the DNS is done using what we call as a spectral method. And what you do is, velocity, and this is instantaneous velocity, is expressed ये क्या हो गया यार? And instantaneous velocity, what's happened? This is expressed in Fourier modes. That is, we write it as sigma over k e to the power of I times k dotted with x times a Fourier transform of u, which is a function of k comma t. So again, no details, just a way that we first express the velocity by its Fourier transform. Now these k's are finite, that means they are integral. They will go from minus n by 2 to plus n by 2 or something like that, minus n to plus n. So they are integers, minus 100, minus 99, minus 98, up to 0, and then up to plus 99. Okay, and we have I k comma x. So this x will be the total domain divided by n, and there's a 2 pi function will come in. And so what you get is, each of these Fourier transform, while this was a function, velocity was a function of x, this transform, for each n you will have one value. u hat of minus 99, u hat of minus 98, and so on. And notice this k is a vector. So this means it will be from, in each of the directions there will be one k, kx, ky, and kz. Okay. So for each of these you have an equation, and when you substitute this in the Navier-Stokes equation, you will get an ordinary differential equation set for each of u hat of k. Because now k is the finite, is a number. So you will get ordinary differential equations in time. And those equations have to be solved simultaneously to get the value of u hat of k. And once you get u hat of k, then you invert it to get u of x. So this is what you do in DNS. This is what is called a spectral method code.
Easier to solve the computationally less expensive.
Well, it does, because one thing is that here, then each of these equations becomes an equation in du hat. It is just an ODE, what you are solving. But then there are so many of these simultaneous ODEs which have to be solved. Now, easier or difficult, there are many things. Well, one is if the velocity field is homogeneous in all directions, then you can use this method. Then you can expand it in Fourier transform. If it is an inhomogeneous field, then you cannot expand along the inhomogeneous direction. You cannot use Fourier modes, because Fourier modes work only for periodic solutions. So there you use some other series like Chebyshev polynomial.
Functions have their Fourier.
So they could have Fourier, but instead of Fourier, more convenient would be some other. So probably what you are meaning by Fourier would be modified Fourier. So that would be something like Chebyshev polynomials for, let's say. So some other series has to be used there.
How many equations do you have to?
So now
That would depend on k.
that would depend on k, and that k would depend on how many you have to resolve up to the Kolmogorov scale. So total length divided by eta will give you n in each dimension. The total flow domain divided by eta is what will tell you how many k's.
That means if I have, let's say, 1000 plus 1000 plus.
It will be, yeah, it will easily be go like that. That's precisely, that's why DNS is not feasible. You have you had for each of them. So, and then you solve together. And that's why when you do DNS, a lot of junk data also comes, because you're resolving till the smallest scales, and you may not need all of that, but it has to be solved for like that. Coupled ODs, bilkul. Billion coupled ODs, exactly. That is what happens in DNS. Okay. So this is, we use a spectral method. Of course, sometimes you may find better ways than u hat. Can we find one of the ways? There is a mode where I have done a lot of work. It's called the proper orthogonal decomposition. So instead of expanding it in Fourier modes, you expand it in what we call as the POD modes. But the problem with that method mainly is, to get the POD modes, you need the data. Otherwise, so you have to start with the data to get the POD modes. So if you have the data, then why do we solve the equations? Experimental or numerical, whatever. But unless you have the data, you can't find the POD modes. POD modes are very efficient in the sense that they capture the maximum energy. So therefore, you don't need to go till very large numbers. The number, yeah, most important contributions will be counted and you truncate it at some step. So the derivation is almost identical. Basically, because in Fourier modes also you realize that these modes, when you integrate with respect to x, if the two modes are equal, then you get a non-zero integral. If they are unequal, then you get zero when you integrate it on domain, because these are mutually orthogonal. So those properties are used. But so this is how DNS is done. Okay. Now, is there something in intermediate? So now first let's talk of, so I just wanted to give what happens in DNS, but if we talk of intermediate modes, then first is what is called Reynolds stress modeling, or why is the ये पता नहीं, येलो लाइन तो आई थिंक कुछ, आई डोंट थिंक दैट इज, बट हो क्या रहा है, पेन क्यों नहीं रहा ये, इसका अच्छा है, लेट जस्ट थोड़ी देर इसको चार्ज लगा, गेट चार्ज, क्या
आप इससे मिलके कनेक्ट कर लीजिए।
अभी हो जाएगा, कोई बात, तुम्हें भी तो लिखना, ठीक है अभी करते हैं, चलो. सो नाउ what I was saying was second order modeling or Reynolds stress modeling. So this is an so here what we do is we had a two equation model, K and epsilon. Now here we have a multi equation model. You solve for each component of ui prime uj prime. Instead of using the eddy viscosity hypothesis, you don't use it. What you do is you solve the equation for u1 prime square, u2 prime square, u3 prime square, and then you will solve it for u1 prime, u2 prime, u1 prime, u3 prime, and u2 prime, u3 prime. So totally 6 equations to be solved. If you are solving all 6, you don't need the K equation, because K will come from u1 prime square plus u2 prime square plus u3 prime square. But you will still need the epsilon equation. So you solve the equation for Reynolds stresses. That is what is done in Reynolds stress model. And these are also called second order models, because you are solving the equations for second order. Now we have derived the Reynolds stress equations. In homework number 2, all of you derived the equation for ui prime uj prime. But we realize there are higher order unknowns. There are many, many unknowns, so each of those terms have to be modeled. In the mid-80s, people thought this was the way to go for turbulence. That we solve for Reynolds stress equations, ui prime uj prime. Instead of using the eddy viscosity hypothesis, we solve for ui prime uj prime. But very soon they realized, and that is why I also got caught in this, in some sense trapped in this approach, was that it was futile, because the number of equations you have to solve now is 6 plus 1, 7 more equations. And if there is a heat flux, then another 3 equations for heat flux, ui prime phi prime, so u1 phi, u2 phi, u3 phi. So you have to solve equations for all those. And then of course Lumley did a lot of work, tried to find out how to make these models. So now I think I can continue. So if I look at this Reynolds stress modeling, so this model, basically we solve the equations for ui prime uj prime, and these equations are of the form, so now you are solving these many more differential equations. This form we have derived in homework number 2. Okay. Now all the circle terms are unclosed. Tijk contains many of these terms. Rij term is basically uj prime p prime. There's a pressure correlation, again it is unclosed. Epsilon ij, we have an equation for epsilon, but epsilon ij is a second order tensor. So then they are unclosed, we have to model epsilon ij we order, we find, put it as isotropic term. So we say is equal to -2, this is epsilon ij is 2/3 of epsilon times delta ij. Epsilon we are solving the equation, so that is how we close this. And then we close these terms. Pij is minus ui prime uj prime dui by dxj. So this is unclosed. This is closed because we are solving the equation for ui uj. So this term is known, but this is how these were solved. So you need six plus 1. 6 is ui prime uj prime. 1 is epsilon equations other than mean velocity and mean pressure. So for simple case, when there is no heat transfer, you have to solve. So you have to solve total of 7 plus 3, 10 plus 1, 11. You have to solve 11 differential equations simultaneously, non-linear equations. And each of them have their own models. So obviously this had to be a futile exercise. Of course, a lot of work was done in 80s, and there used to be these conferences where there were competitions for turbulent flows, that which model performs the best. And obviously, and since because we ui prime uj prime, you are solving, getting some more physics because of these equations, these models do perform better than k epsilon, but the effort involved is too big. So that is why they have sort of now more or less very few are using them.
Is it a diagonal matrix?
So because then we epsilon ij we write it as so we write it as 2/3 epsilon delta ij. 2/3 या 1/3 जो भी है मतलब. So then, and we are solving the equation for epsilon. So this becomes a. So, but these are more or less, now we don't sort of talk too much about. This is called Rand's models or second order models. Okay. Now, one of the ways, and this is the last in the models which I will do, is, and again I'm just throwing names, I'm not solving it anyway, is, and a lot of now if the flows are complex and you don't want to use k epsilon model, then the whole world is moving towards what we call LES, and these are large eddy simulation. In LES, the larger scales are solved, the smaller scales are modeled. If I look at this definition, then even Reynolds average Navier-Stokes equation in some sense do this. They solve the larger scales, the mean velocity, and the smaller scales are modeled. But here this is done to a much finer level, and LES is in between second order models and DLS. And what is done in LES is the one which I just discussed. Second order means you're solving for ui prime uj prime. So that's why it's called second order. Ui prime uj prime is a second order statistics. Now in LES, again, without going in the details, the first thing which you do is you filter the equations. It's something like taking the averaging, but it is different. What we do is we decompose ui of x comma t as into, or we decompose into two parts. We filter this equation. So therefore, there is a filtered part of ui. And this filtered part is still a function of x and t. And there is a residual part which is there. And the way the filtering operation is done is there is a filter which is a function, and you integrate ui of xt with that function over the entire volume, and the resultant is called the filter. Now, as opposed to the Reynolds averaging, the average of this residual is not zero. And this quantity is a function of both x and t. So this filtered velocity is what we solved for. Whatever residual terms come, they are modeled. So the residual terms will again come in the form of something like Reynolds stresses. They will not be Reynolds stresses because the average of ui of residual is not zero. So you get terms like that, and whenever the residue terms come, they are modeled. So you essentially are solving only for the filtered field, and which is better than DNS or less cumbersome than DNS because you do not go up to the level of eta. This is a larger velocity which you are solving. So somewhere in the energy containing range you solve. So DNS is also done in a large way using spectral type of methods. I don't know what they are using now, the group. अभी जो तुमने देखा है वो लोग कैसे कर रहे हैं, I have no idea. नहीं, वॉल तो लगाया है, but are they using spectral methods or are they using finite difference, finite volume type? मेरे ख्याल से spectral ही कर रहे हो क्या? I don't know. So in fact now we will be working on some part of LES. I have never worked on LES, so I'm not very clear how it happens. But basically a filter is used and we solve equations for this. So that's what. So that common average was basically an ergodic mean. You took many observations just to come in. Here this ui bar is basically something like, if there is a filter g of x prime, then you have ui of x comma t dx. This is what ui bar is. It's some, so I'm not, it may not be a very exact equation, but this is a filter, what you call as a filter. So it's something like you multiply this with a filter and average it out. And that is what gives you the ui bar. So bar ui bar. इसको ठीक कर दो. क्या हो गया, फिर चला गया लगता है. So anyway, this is ui bar. It's some sort of a, again here, this sort of an integral, when you calculate, it will have its own nuances how to calculate this and all. So whenever, so I think it's probably dx prime here also. I'm not sure. So there are some, probably this is also dx prime, something like this. I think it's d charge तो है, ये dx prime होता है, it's integrated over there. So this is how, again, as I said, I'm not even well versed with LES, so I'm just wanted to tell you that this is the way a lot of complex flows today are being addressed are by LES. Okay. So now I think with that we'll call an end to the course. So GA filter बोलते हैं इसको. अब ये x prime मेरे पास अभी बुक नहीं है, आई कांट. दैट्स व्हाट आई सेड कि देयर मे बी सम एरर्स इन दिस. कहाँ x है, कहाँ x prime है, आई एम नॉट वेरी श्योर ऑफ दैट. And actually it is very ironical that to model this you will get terms like ui prime, uj prime residual, and we use again an eddy viscosity type of model to model the residual stresses. The residual stresses are used, in fact I think those stresses are called as Leonard stress. Some of the older papers they refer to it as, so one is Reynolds stress, the other is Leonard, Leonard, Leonard stress, based on the person who must have. Those who take the course in turbulence modeling, which is floated next semester, they may find more of this last part in much more detail. Well, I tried to cover the eddy viscosity part in detail because we use the eddy viscosity model. So, okay. अच्छा, अब now एक तो होमवर्क कभी कितने लोगों ने नहीं किया है? नहीं किया अभी, कल तक दे दोगे? तो जिन्होंने अभी किया है देना चाहते हो तो दे दो, अदरवाइज टुमारो गिव इट टू प्रकाश और अल्ताफ. अल्ताफ आ गया आपका, ठीक है, गिव इट टू अल्ताफ को दे देना. वैसे भी प्रकाश इज ऑडिटिंग द कोर्स, सो मतलब इट वोंट लाइक टू, तो गिव इट टू अल्ताफ. आई थिंक तो लैब पता है सबको कहाँ है, नहीं तो प्लीज आस्क हिम वेयर ही विल बी, बट गिव इट बाय टुमारो सो दैट देन आई कैन प्रिपेयर द पीएमटी एटसेट्रा. हाँ अभी दे दो, अभी कर दिया तो अभी है तो लाए हो तो दे ही दो, नो इश्यूज. ओके, नाउ ये बंद कर दें. अबाउट द एग्जाम पार्ट,